Student at home, is another wonderful time on School on Air, and today in physics we'll be talking about capacitors and capacitance. I'm very sure that you must have seen a capacitor before, especially in some of these household electronic devices like your transistor radio. You see them now. So the capacitors generally now, we use them in storing charges now, and they are of great importance to us in physics. But quickly now, let's quickly look at what that word capacitor means. The capacitors are devices for storing electronic charges. They are devices that we use in storing electronic charges, and they are very important because if you have a device that doesn't have a capacitor, definitely now there will be a problem, as that's to do with storage of charges and then the dissipation of that energy for that electronic devices. For example, if you're having a kind of radio or transistor radio, or some of these electronic devices now that is having a faulty capacitor, there are two things. It's either the device is actually not working properly, or in the case, or it will be working in such a way that it will not be performing to its maximum capacity. So generally now, we talk about capacitor now, we said it that it is for storage of charges. But then the other word there, another key word, is the word capacitance. What does it mean? The capacitance of a capacitor is defined as the ratio of charge, Q, stored by the capacitor to the potential difference, V, between the plates. The ratio of the charge, Q, that's the charge on the capacitor, to the potential difference, V, between the capacitor plates, is what we refer to as the capacitance. But then what do we mean by that plates? In the plates of a capacitor now, we are going to look at how a capacitor will look like in terms of construction, and we are going to go into that later. But to start with now, in physics also we talk about the units and dimension, and in capacitance now we have units for capacitance of a capacitor. The capacitance is measured in farads. The unit of measurements of capacitance is in farads, but most time now we use the symbol F to shorten it off to make our work easier, and so we use symbol F now. But there are different types of farad in terms of units, just like we have in the case of length. You know, we talk about centimeter, millimeter, decimeter, and all those ones. But in the case of capacitance too, now we talk about microfarads. 1 microfarad, and you can see the symbol that we use there now. 1 microfarad is equals to 10 raised to the power minus 6 farad. That is about 1 over 1 million farad. So 1 microfarad now. So if you are given a question under exam condition and they inform you that the unit of the capacitance is 1 microfarad, definitely it is also equals to 10 raised to the power minus 6 farad. Or we can also mathematically represent it as 1 times 10 raised to the power minus 6 farad, knowing fully well that 1 times 10 raised to the power minus 6 farad is also 10 raised to the power minus 6 farad. But apart from talking about microfarad, we can also talk about what we refer to as nanofarads. The micro is 10 raised to the power minus 6 farads, but the nanofarad is represented by this. You can see 1 NF, and that is equal to 10 raised to the power minus 9 farad, or 1 times 10 raised to the power minus 9 farad. You can see the micro is 10 raised to the power minus 6, while nanofarad is 10 raised to the power minus 9 farad, which means that nanofarad is smaller than microfarad. Then we also have the picofarad, which is the smallest of all, which is represented by 1 PF, and 1 picofarad is also equivalent to 10 raised to the power minus 12 farads. Microfarad 10 raised to the power minus 6 farads, nanofarad 10 raised to the power minus 9 farad, picofarad 10 raised to the power minus 12 farads. And these are very important because in questions that has to do with capacitance now, we used to introduce this to shorten form to make it easier for us to actually answer questions. So it's very important for you to actually know these units of measurement and their conversion when you are doing your calculation, as it has to do with capacitance of capacitor. But then generally now, capacitance C of parallel plate capacitor is also given by, when we look at the capacitance of a capacitor, we represent it mathematically as EB equals to this permittivity constant, which we refer to as E, multiplied by the area of overlap divided by the distance between plates, M. So you can see that the capacitance of the capacitor is directly proportional to the permittivity of a material which we represented by this symbol E, and the area of overlap of plates are divided by the distance between the two plates. Because in a capacitor now you're having two plates. So we want to look at you have to look at the area of the overlap of those two plates, the area which they overlap. You also need to determine the distance between those two plates, as well as the constant, which we call the permittivity of material. So the product of the permittivity of material and the area of overlap divided by the distance between plates will give us the capacitance of capacitor. But don't forget that when you even determine the capacitance of a capacitor, the unit, like I said earlier on, will be in farad. And the area, of course, is always measured in meters squared. So if you are given a question that is in centimeter, of course, you should know what to do. But you have to do the unit of conversion. You have to do the conversion of that unit to meter squared, because the area of that overlap of plates is in meter squared. Also, the distance between plates is also measured in meter, like length is measured in meter, while the permittivity of materials between those two plates is measured in farad per meter, or capacitance squared per Newton meter squared. So generally now, capacitor consists essentially of two conductor metal plates. Like I told you now, a capacitor is made up of two plates, two conductors metal plates, just like you're having two parallel plates facing each other. So the metal plates now are separated by a small distance. The metal plates are separated by a small distance by an insulator. So you're having two plates, two conductor plates, and between them now, within a short distance between them, you have an insulator. And you will recall from that formula that we actually used, I told you that the distance between them is always measured in meter, but distance generally now is not too far, and between those two distances we have an insulator between those two plates of conductor. So you take note of the fact that in capacitor now you're having two conductors metal plates, and they are carrying opposite charges. So one of those plates is going to be positively charged, while the other one is going to be negatively charged. Two conductor metal plates of opposite charges, and the metal plates are separated by a small distance, which is occupied by an insulator. But then when you talk about the insulator that is between the two plates of conductors in the capacitor, then what are the components of that insulator? What is it supposed to be? One of the components of that insulator. Actually, the insulating material placed between the plates of a capacitor is called a dielectric substance. The insulating material, that particular insulator now, and the material of which it is made up of, the insulating material placed between the plate of a capacitor is called a dielectric substance. I hope you won't forget this. We have two plates, metal plates of opposite charges, and they are about a small distance. The distance between them is not too large, and then you have what we refer to as a dielectric substance, which is an insulating material between two plates of a capacitor. And generally now, the capacitance increases with the area between the plates. As the area between the plates increases, the capacitance increases with that area between the plates. So the bigger the area now, the more the area, the more the capacitance between those two plates of a capacitor. And the capacitance also decreases with increasing distance. As you increase the distance, there will be decrease in capacitance. You know, and you remember that I was saying it at the beginning, that the distance between those two plates are not going to be that large, because the larger the area now, the more the distance between those two plates, then the lower the capacitance of a capacitor. So you take note of those factors that will affect the capacitance of a capacitor. The first one is the fact that the area now, the capacitance will increase with the area. So the larger the area, the more the capacitance, but it will decrease with increasing distance. So the more the distance between those two plates, the lower the capacitance. And then the capacitance will also be affected by the insulating material, which we refer to as dielectric constant. The capacitance will increase with the dielectric constant. So that if you have more insulating material between the plates of capacitors now, what you will end up having is an increase in the capacitance of a capacitor. I hope you have been able to take note of these factors that will affect the capacitance of a capacitor. Like I said, the first one is that the capacitance will increase with the area between the plates. It will decrease with increasing distance, and it will also increase with the dielectric constant. And then generally now in physics also we have a symbol for capacitor. You can this is the symbol of capacitor, and you can see that now. Like I said, that it's made up of two plates that are opposite charge down. So one will be acting as a positive plate, and the other one is acting as a negative plate. And you can see that accordingly in the second diagram. You are having the metal plate. This is the positive plate of the capacitor, and you can see the negative metal plate of the capacitor. And between them, there is a distance between them, which is going to be occupied by the dielectric material, which we refer to as an insulating material. And the two are connected to the cell. So you can see that we have a symbol for capacitor made up of two plates which are of opposite charges and at a particular distance between them. So, like I said, that the unit of capacitance is the farad, and we have talked about the microfarad, picofarad, as well as nanofarad. But the capacitance of a capacitor is 1 farad if 1 coulomb of charge is transferred. The capacitance of a capacitor is 1 farad if 1 coulomb, that's the charge, of charge is transferred from one conductor to the other per unit volts of potential difference between the conductor. So by definition now, you can define the capacitance of a capacitor as 1 farad. It is 1 farad when we have 1 coulomb. Capacitance will be 1 farad when the charge is 1 coulomb, and that charge is transferred from one conductor. As you know, we are talking about the two conductors now, two metal plates. When the charge is transferred from one conductor to the other per unit voltage of potential difference between the conductor. So generally now we talk about capacitance now. Since we said it's measured in farad now, the capacitance generally now is going to be equal to the charge all over voltage, and the charge is always measured in coulomb, and the voltage is going to be equal to what? The voltage is measured in volts. So 1 farad of capacitance will be equal we arrive at when the coulomb is 1 as well as the voltage is 1. That's exactly what that definition is actually talking about. And in case of capacitance too, we will talk about the microfarad, in which case we are talking about 10 raised to the minus 6 farad. We also talk about the picofarads when we talk about the 10 raised to the minus 12 farads. So this is the unit of the capacitance of a capacitor. But then the value of the capacitance depends on the following. That is, the value or the numerical value that we end up having in terms of capacitance will depend on the following. It will, like I told you, depends on the size of the capacitor, the shape, and distance between the distance separating the two plates. The size, shape, distance separating the two plates. The value of the capacitor may also definitely depend on the nature of the material that separates them. The material that separates them. That material we refer to as a dielectric substance. The capacitance of a capacitor will also depend on the area of the plate, or we call the common area of the plate. So generally now today we have talked at length about capacitance of a capacitor. We have also been talking about the capacitor itself. And at the beginning, when I told you that a capacitor is something that we've always been using at home in most of our electronic devices. I also made mention of it that in the case of capacitor now, for us to construct a capacitor, we actually need two plates, two conductors. One is actually, and they have opposite charges. One is a positively charged plate, while the other one is a negatively charged plate. And I told you also that between those two plates, the positively charged plates and negatively charged plates, we have a space and a distance between them. And that distance is always occupied by an insulator. And that insulator now is made of material called dielectric substance. We talk about the capacitance of a capacitor, and I was telling you at the beginning now that there is no way we will not be in need of a capacitor. They have a great or immense benefit to mankind. You see them in some of our modern electronic devices. They are very important in storing charges, because by storing those charges now, it makes it easier for us to actually utilize some of those electronic devices. So we talk about the radio, you talk about television, you talk about some of these household equipment or devices that we use at home. So generally today we've been talking about capacitor, like I told you, and we said it, that a capacitor is a device for storing electric charge. We've also been talking about the fact that the capacitance of a capacitor is the charge per unit potential difference. That is, there's a link up, a relationship between the capacitance of the capacitor and the charge. The capacitance of the capacitor is directly proportional to the charge and inversely proportional to the potential difference. And you will also take note of the fact that I have also made mention of the fact that the unit of measurement for capacitance is farad, and we have different farad. We talk about the picofarad, we talk about the microfarad, and all those other ones. Then the capacitance of a capacitor is the charge, like I told you, per unit potential difference between the plates of a capacitor. So capacitance generally can also be mathematically represented as C being equals to Q all over V, where Q is the charge and B is the potential difference. So, dear students at home, I hope you have been able to learn one or two things from today's episode, and I hope that along the way now, when we continue talking about this now, you will learn more things as it has to do with capacitors and capacitance. But before we go, I want you to take note of the assignment that is on the board. The assignment is asking us to do, it said, what is the total capacitance in the circuit represented by the diagram above? The total capacitance can always be, capacitance now may be in series, or they may also be in what we call parallel. But when they are in parallel now, we assume that they are in series, like resistors, we add them together. But when they are in series now, we assume that they are in parallel form, and we find them in, like the case of a resistor. Dear students at home, we have come to the end of today's episode. I hope you'll be able to learn one or two things, and I hope you will join me next time when we continue talking about this topic of discussion. From me, have a wonderful day.